So today we'll be going over how to use the Diablo Real Time Gas Analyzer, and as the name suggests, it allows you to analyze gases in real time. There are sort of two main components to the RTGA. There's on the left the mass spectrometer, which is what we use to detect the gas, and on the right is the RTGA interface. So a couple of main parts of the real-time gas analyzer are this multi-wave valve over here, which is the sampling interface into the RTGA, and then there's this isolation valve, which is what allows your sample to enter the mass spec, but it's also the sort of the last line of defense for protecting the mass spec. And there's also this pressure sensor, which allows you to measure the value of the RTGA interface here and lets you know if you're flowing sample through or not. So the two gases we have hooked up to the RTGA are right here. So the far left is a 50-50 mixture of hydrogen and argon, and in the middle we have a 100% helium tank. And we'll use the two gas tanks to calibrate the RTGA and the mass spec for our samples. And the regulators should be set at the appropriate pressure. So when you turn them on, all you should need to do is open these main gas supply valves for the cylinder, and you shouldn't have to adjust the regulators at all. The RTGA has primarily been used for the Energy, Materials, Devices, and Systems course, and primarily for the photocatalysis module of the lab. And in that lab, we are trying to measure photocatalytically produced hydrogen gas. And so we use these gas-tight vials that have these screw-top caps with septa on the top. And it's important that when you're sampling your materials or your gases, that you only sample the headspace of the material. You do not want any liquid to go into the RTGA, because that can end up clogging it. When you're using these stainless steel tubing as your sample inlet, it's important to always stay in the headspace of your vial. So the computer we use to run the RTGA software is to the immediate right of the instrument, and so make sure you reserve the appropriate time on Coral and enable it to start running your scan. So the main software we use for the RTGA setup is this MS Sensor 3.0 software. So if you double click, it'll open. This window is basically an event log, and so it's only really important if you see something show up in red, which means that there's an error with the instrument, or in yellow, which is a warning that there may be something wrong with the instrument. But as you can see here, there are no errors and no warnings. Most of the options you'll be tuning or messing with will be in this toolbar. So if you hit this acquisition button, it'll open this new window, and this is going to be your primary interface with the instrument. But before we get too much further into that, I'm going to briefly cover how to tune the mass spec, especially for hydrogen. So tuning is essentially trying to find the local minima in the mass spec for, so you're essentially calibrating it. And this is something that doesn't need to be done too frequently, but maybe once a month or so. To tune, you'll go to the edit method, and the primary method we use for the EMDS course is this UW calibrated H2 monitor, because we're trying to measure photocatalytically produced hydrogen in the course. So if you hit OK, it'll give you this new window where you can start to mess with some of the method values. So in order to tune, we'll open this instrument section, and what we want to tune is the actual mass spec. So if you right click here and edit the instrument, you'll see under here it has a current tune file loaded, and that we can open the tune window. If you open the tune window, it'll open this Agilent software. And so the MS sensor in the background is actually a Diablo software, and this software that just opened is an Agilent software, and the two communicate in order to get the data that we're trying to measure. You can go under hydrogen and do a full hydrogen tune. So this will do the regular tuning process in the mass spec with its built-in standard, and then it'll also do a second portion where you flow hydrogen through the mass spec, and then it tunes a second time. So when you click full hydrogen tune, it'll prompt you to make sure that the RTGA is configured for hydrogen, which it is. We have the appropriate low Gauss magnet. Hydrogen is flowing, and is the RTGA isolation valve open. Before we continue, we want to make sure that the gas is on and that we are flowing it into the mass spec. The hydrogen gas we'll be using is from this 50-50 aragon hydrogen mixture on the left. We'll just make sure that this main supply valve is on, and then once the gas is on, we need to open this multi-way valve to the appropriate gas line. So as you can see right now, it's currently pointing to a cap, so it's sealed. And what we want to do is we want to open it up to that 50-50 mixture. It's a little hard to see in this video, but that's the one directly to the right of it. When we open the multi-way valve to the appropriate gas line, you should see that the pressure increases pretty significantly, because now we're flowing gas into this interface. And then all you want to do is open this isolation valve, so that allows your sample to actually enter the mass spec. So now we know that hydrogen's flowing and the isolation valve is open, so we can just hit yes to continue the tune. And the tune is basically completely automated, so you basically just need to let it run to completion. And so the first part is, again, that auto tune process where it'll use the built-in internal standard in the mass spec, which is this PFTBA. And so once that goes, you'll start to see some signals. When the auto tune is done, it'll open this file saving window, and so it'll actually auto save as just atune.xps. But what I like to do is I also like to save an extra file with the date, just so that we have a record of all the tune files in case something goes wrong. We can load an older tune file to recalibrate the instrument. So we'll do atune 180404. And once you save that, it should then start the hydrogen tune. So you can see here, this low mass peak has changed to 2 AMU, so that's sampling for hydrogen or measuring for hydrogen. But if you look closely, every now and then you'll get this peak that is basically at 0. And this is sort of an intrinsic issue with trying to measure hydrogen through mass spec. So from my understanding, this is called a zero blast measurement issue, where essentially the hydrogen molecule is so light that sometimes the detector thinks it's just noise. And so you can see again that we do get a peak at 2.2 for hydrogen, but every now and then that peak will disappear and we'll just have a peak at 0. And so when we try to measure hydrogen, we adjust our calibration curve for this appropriately. And if you have an issue where you don't see any peaks at 2.2, you can just increase the pressure on that hydrogen argon regulator to increase the sample flow a bit. So now that the hydrogen tune is done, we will save another htune file. So again, we'll do 0404. And so our tune is completed. So these are actually tune reports. So we will save that. And so that's just a record of what tunes we've run. But what I like to do as well is to save the hydrogen tune parameter. So you can see it automatically saves under just this htune.u file. But I also like to create a secondary file just to have a backup. In case a future tune goes wrong, we can just reload this old one. So we'll save that. So now that the tunes are done, we can close this, go back to our MS or sensor software, and we will load our new tune file, which, as you can see, has been created today. We'll open that, we'll save, and we will close the window. So now to run your sample, we'll create a new data file. And so just for the sake of this video, we'll name this test video. And so you can see here that all of the, or most of the options under this acquisition window have been grayed out. And that's because we need to first turn on the mass spec as well as the pressure sensor. So we'll hit initialize instruments, and that's basically just connecting, again, that pressure sensor and that mass spec to the computer. And this will sometimes take a couple of minutes. But as you can see, as the Agilent mass spec is connecting, it'll reopen this window for the Agilent software. So now both instruments are online, and so if we hit initialize acquisition, this allows us to say who the operator is, what the sample name is. So we'll just do test video, and you can briefly do a sample description. So testing for SOP. And we will hit OK. So now that will open all of these new windows, which will be what we use to actually view our data in real time. And so if you would like, you can reorder these by just tile vertical. And so now when you have the green light, you can actually run your sample. So what I like to do is I first like to make sure that the isolation valve and the multi-way valve are open to the correct sample, and then I'll hit start. So we get the real-time data here, the actual values, and for this method we have a calibrated argon value, a calibrated hydrogen value, and a calibrated helium value. And those, you can tell, are quite off. So it's supposed to be a 50-50 mixture of argon to hydrogen, and it's clearly not. And we can see this in a plot form over here. So the red is the argon, the green is the hydrogen. So we need to actually collect this data for a couple of minutes so that we can run our calibration. And actually the hydrogen values are quite noisy, so I'm actually going to increase the hydrogen pressure a bit just to see if that levels out. But again, these sort of drops to zero are part of that zero blast issue I was talking about earlier when trying to measure hydrogen, where the molecule is so light that sometimes the detector treats it as just noise. So we'll collect this data for a few minutes because we will take these raw hydrogen and argon values. So these raw argon and hydrogen values, so we can create our calibration curve. But we're basically doing a 2-point calibration curve. So we'll have 1 point for 50% argon. We'll have 1 point for 50% hydrogen. And so now we need a second point. And our second point will be the helium, which will give us 0% argon and 0% hydrogen. So now that we've collected a few minutes worth of data, what I'm actually going to do is I won't stop the scan, but instead I will just switch the multi-way valve to the helium tank, and you should see that the pressures will change in real time, or the values will change in real time. So as you can see here, once I switch that multi-way valve, that helium value in yellow immediately jumped up, and then the argon and hydrogen values immediately drops down to 0. Again, and we're measuring all of this in real time. So we'll collect this helium measurement for a few minutes as well. And then we'll do our calibration. Great. Now that we've collected about 3 minutes worth of data for this helium, we can stop the acquisition. And it's important to turn off that isolation valve on the RTGA once you're done running your scan, because this is the sort of last line of defense in protecting the mass spec from getting damaged. And we can also close our multi-wave valve. So we've collected some data now, but our method is not appropriately calibrated. So what I like to do, or what you need to do to calibrate, is to go into your RTGA data. There's a shortcut on the desktop, as you can see here. You'll find your sample, so we'll do this test video. The data is contained in this CSV file. So as you can see here, it's plotted, and we have columns for our argon raw values in column H, our hydrogen raw values in column M, and those are sort of the main two columns we will be interested in. So what I actually like to do is I like to just make two sections on my Excel spreadsheet where I'll say I have an argon value of 50 and an argon value of 0, as well as a hydrogen value of 50 and a hydrogen value of 0. So for the argon value of 50, all we do is we average our raw values. So we'll just go from the start. And you can see around here the values drop down pretty significantly, and that's when we switch to the helium. So I will usually sort of remove those last few values from the average, just because that's while we were transitioning into the second gas. And we'll hit enter. We'll do the same thing for our argon 0 value. And so similarly, we'll scroll down to the appropriate time change, as you can see here. So we're going to average these values for the 0 of our argon, and I'm not actually going to average these values in the few hundreds because we had a bit of a technical difficulty while running our last scan. But now we have raw data values for 50% argon and 0% argon, which will allow us to make our 2-point calibration. It's a little more involved with the hydrogen, because as you can see here, we're getting these random 0 values, and again, that's from that zero blast issue with measuring hydrogen. So what I like to do is I actually will select all of the data that of the hydrogen run, and I'll actually copy and paste it into a new column. And then we basically want to ignore all of these 0 values in our average. So what we can then do is we can sort our data by going to data, sort, and we'll sort it from smallest to largest. Well, actually, let's do largest to smallest. And that way we can average everything except those 0 values. And so we'll actually do the same thing for the 0s on our hydrogen, because again, these 0 values are not indicative of actually hydrogen. That's just the software detector basically saying that there's no value there. So now we have 2 points for both our argon and our hydrogen. So we can go back to that MS Sensor software. We'll edit our method. and you'll be prompted that we need to return the instruments to offline, which is fine. And then you'll go into the signals window, and we'll adjust our calibrated aragon, which we'll right click, and we'll hit edit signal, and we'll hit calibrate. And so now we can enter those values that we just calculated in our Excel spreadsheet. So 60.1, or just 60 for our 0 value, and then 32498 for our 50 value. And we'll hit calculate, so we have a new line for our calibration curve, and we'll hit save, and we'll hit save again. We'll do the same thing with our hydrogen calibration. So our 0 is this 120 value, I guess 121, and our 50 is 34561. We'll hit calculate, again we have a new curve, we'll save, and when you close this window, you'll be prompted to save your method, which again you want to save so that because we've created new calibration curves. Now what I like to do is I like to create a new data file saying that this has been calibrated. I'll initialize the instrument, and part of why I do this is because the software will sometimes crash if you try to rewrite any old data. So we can reinitialize the instruments. We'll initialize the acquisition. It'll sort of refresh all of these windows. We can tile them again appropriately. We'll wait for the mass spec to have the green light so that we can run our scan. And now before we hit start, we want to reopen our multi-wave valve and our isolation valve to the 50-50 mixture. And now that that's been done, we can hit start. So as you can see, our calibration wasn't quite perfect, so it's not quite the 50-50 mixture we want. So we did have some technical difficulties in running that last scan, but if we wanted to, we could run a second set of calibrations. But it seems to be sort of correcting itself as we let it run a little longer. Yeah, and so now that we've let it run a little longer, we can see that the values are a little closer to what we had anticipated. But again, if we would like, we could run another calibration. And then just to give you a brief visual of how we run or how we sample from this gas type vial in the EMDS course, all we typically do is we will change to this sample tubing, which is on this far end of the multi-wave valve. And so right now this is sampling just room air, and if you look at the RTGA or the software, you should see that the pressure has dropped pretty significantly, and that now we have 0% argon and 0% hydrogen. And all we typically do is we will just puncture the septa. So we'll just puncture the septa of our gas tight vial with this stainless steel tubing. The gauge of the tubing is a little thick, so sometimes it requires a bit of pressure. And again, it's really important to note that depending on how high your solution height is, you only want to sample the headspace. So we basically punctured the septa just like that, and we'd sample the headspace for a couple minutes, analyzing what the composition of that gas, or of that headspace is, the gas composition. And so it's also important to note that the RTGA gives you values in percentages. So how I've had the students calculate sort of mole values for their lab, or their lab reports, is to use this equation, which is assuming that the original pressure of the headspace was atmospheric, and that any increase in pressure is due to hydrogen that's been created or generated. And then you can essentially back calculate using the ideal gas law. So when we're done with our measurements, we can hit stop. We will close the isolation valve and the multi-way valve, and then we will also close the gas cylinders. And if you need more assistance on running the RTGA, or if you would like written instructions, there is an SOP on the desktop under this RTGA workflow, which has screenshots and step-by-step instructions.